again to the project Amor ICMI, our DIS multimedia online resources. Having defined mathematics as the activity of telling stories about mathematical objects, I will be pondering in this module about this later term, mathematical objects. The issue is not a simple one. While dealing with objects such as those investigated in physics, biology, or astronomy is pretty straightforward, we can experience these objects even before being able to say anything about them. The case of mathematical objects is quite different. Numbers, functions, and derivatives, unlike stones, stars, and living creatures, do not wait for us out there to be seen, smelled, heard, or felt. If so, what are these objects called mathematical? Where can we find them? And how can we get aware of them and their properties? I will now try to address all these questions. But first, let me return to where the previous module ended. As you may remember, in the last module, I asked, what is mathematics? And my cognitive answer was that it's a kind of discourse in which we tell stories of mathematical objects. In this claim, I followed in the footsteps of such leading thinkers of the 20th century as the sociologist Basil Bernstein and the philosophers Richard Rorty, Jean-François Lyotard, and Michel Foucault, all of whom claim that knowledge, whether biological, historical, scientific, or any other, is a form of discourse. Thus, for instance, Foucault claimed that discourses are things said. These are those familiar yet enigmatic groups of statements that are known as medicine, political economy, and biology. This is what he said, and I will now add mathematics to this list. This cognitive definition, let me read it again. Mathematics is the discourse in which we tell stories on mathematical objects. This definition may appear compellingly simple and clear, but it leaves one crucial question unanswered. Mathematical objects, what are they? Some of you may wonder whether this question should really be asked. As we know only too well from history, this kind of conversation is likely to result in consternation, perhaps even embarrassment. Research mathematicians remain mostly silent on this issue. Just like a juggler keeps different objects in the air without bothering about who made them and how they did it, so does the explorer of mathematical universe juggle numbers, triangles, and sets, happy to have them in her or his world, and without asking who brought them there or how and by whom they were made. In consequence, the issue of the origins and nature of mathematical objects remains an elephant in the room in which mathematics is done or learned. I believe that leaving things unexplained is unhealthy. As I see it, engaging with the question of what mathematics objects are is important because the answer, whatever it is, may impact the way we understand learning mathematics and thus also the way we teach. In this module, I will argue for the cognitive definition according to which mathematical objects, unlike those we encounter in everyday life, do not pre-exist the stories we tell about them, but are rather discursive constructs created in the act of storytelling. This may sound confusing, I know, but I will now try to clarify. More specifically, I will address 4 issues. What are mathematical objects? Why do we need mathematical objects? How are mathematical objects constructed? How do students learn about mathematical objects? I will do it in 2 parts, with the present module devoted to questions 1 and 2, while questions 3 and 4 will be dealt with in the next module, module 5. So what are mathematical objects? But there is a preliminary question. Why do we even speak about mathematical objects as if they were some mysterious, separate ontological category? Aren't numbers, functions, sets, and geometric figures simply signifiers, that is, words or written symbols that we use while talking mathematically? But wait, if mathematical objects were just signifiers, why would we say such things as these signifiers, you can see those red signifiers on the left here, represent the same number? Or that these three signifiers here represent the same function, the basic quadratic function? If these signifiers were mathematical objects, why would we say that they only represent mathematical objects? When we say that something represents something, we imply that there are two things, not one, with one of them, in this case, the number and the function, being the real thing, and the other, the signifiers, only their shadows, their tangible avatars. But if mathematical objects are not signifiers, what are they? So what are mathematical objects? Known answers range between two poles, the dualist, according to which there is an independently existing object that is only represented in the signifier. This answer is known as Platonic or realist. According to the other non-dualist cognitive answer, mathematical objects exist only in discourse. These are discursive devices we introduce to help us tell stories about some phenomena. The dualist approach can also be called traditional. After all, the vision of mathematics as something that is being expressed in discourse is entrenched in the way we speak. For instance, we say that discourse helps in learning mathematics. Many mathematicians express their Platonic beliefs explicitly. Consider, for instance, the following statement by the French mathematician Alain Cohn. Conceptual tools, he said, signs, representations, are not to be confused with mathematical reality itself. So there is mathematical reality and there are tools, two separate things. The non-dualist perspective presents mathematics as a way of communicating, one of many different forms of communication we are able to participate in. Those who adhere to this non-dualistic position would say that discourse helps in learning mathematics. They wouldn't say that discourse helps in learning mathematics. They would say that discourse is exactly what is being learned in mathematical classroom. Let us try to understand where this difference in talking comes from. I will use a comparison. Here are 4 pictures about which I claim that they all represent the same person. You may even recognize this person. It is Sigmund Freud at different points in his life. My question now is this: what is it that makes us say these pictures present the same person? And the answer is simple. We say that these pictures present the same person because a single person served as a model for all 4 of them. Now, let me switch to the following 6 pictures. Here, too, we may speak in terms of a single thing being represented in different ways. All these pictures represent the number 5. But where is this number 5? The truth is that the only common feature of the 6 figures is the following. If we count their elements, we end in all these cases with the word 5. Thus, what makes them in a sense the same is the 5 words long process of counting, and not any common object, as was the case with Freud's pictures. It is precisely because of this fact, that we always end the process of counting with the same word 5, that we all learn to accord such different things as the fingers of one hand, the polygonal building in Washington, and a set of apples with a certain, and also a certain star with the common name 5. This also explains and justifies the famous claim by the French mathematician Henri Poincaré that mathematics is the art of giving the same name to different things. In short, numerical thinking begins with reciting the sequence of sounds known as number words. It is only at a later stage that we shorten the counting to the last word obtained in the process and eventually start using that number word as if it was a name of some independently existing object. Such object, in this case called number 5, is implied to be presented in all these very different images here, the way Freud was presented in the 4 photos. The words "as if" I used in their description signal it may be justified to say that the number is but a metaphor. Another way to say this is to describe number as the objectification of the process of counting. The word objectification, in turn, may be defined in the following way. Objectification is a special type of metaphor. It is a discursive transformation that makes us use mathematical words and symbols as if they signified discourse-independent objects. This transformation involves 2 moves. First, there is nominalization, that is, the act of replacing specific portions of text with a single noun. This is what you do, for instance, when you replace talk about the process of counting with number words used as nouns. I will elaborate on this transformation in the next module. Second, there is alienation, that is, the removal of the human subject. Thus, instead of saying, when I add 3 and 4, I get 7, we now state shortly, 3 plus 4 equals 7. And we now use the new noun as the grammatical subject, signifying an entity that does its own thing with no human agent involved. Just look at how impersonal this second expression, 3 plus 4 equals 7, is in comparison to the first, the one that includes the personal pronoun I. Only when we adopt this form of speech, we say that the signifier, the word or symbol, represents the object. Let me add that objectification is a common phenomenon in almost any discourse, not just in mathematics. We build on the metaphor of a physical object also when we speak not just about function, number, or set, but also on velocity, energy, identity, class, or human ego. Or even about fantastic beasts populating the world of Harry Potter. All this, as any metaphorical extension, preserve some features of the source and lose some. I will now elaborate on what we gain when introducing mathematical objects. Actually, I'm going to make two claims now. First, I will argue that objectification allows us to express ourselves more succinctly, to say more in fewer words. My second claim is that it improves or widens the range of things we can do. Let me begin with the first of these propositions. To make my first point, let me take a look at this symbolically presented mathematical narrative. I can read it in words as follows. If I extract a square root from x and raise the result to the third power, I get the same result as when I raise x to the third power and extract square root from this. But I can also read it in this way. The third power of square root equals square root of the third power. What is the difference between these two formulations? When you look at the words in red, you realize that the expression on the left is mainly about human operations. I extract, I rise, and so on. Whereas the one on the right is about objects, third power, square root, etc. Thus, this one is objectified, whereas this one isn't. And there is also another difference, one that is visually obvious. The objectified statement of the right is much shorter, more concise than the one on the left. Thus, this example clearly corroborates my point. Objectification allowed us to say what we wanted to say more briefly. To illustrate this last claim in an even more dramatic way, I will engage you now in a thought experiment. Here it is. Suppose you cannot use number words 1, 2, 3, except in counting. How would you then present in words the general truths expressed in this equality? 3 plus 4 equals 7. Let me explain. You can use the number words, but only as words. Thus, you can say, I counted the marbles in this box and got 5 as the last number word. But you cannot say, there are 5 marbles in this box. I suggest that you give some thought to possible answers, and I will return to this theme in the second part of this module. You will then be able to compare your response to the one I am going to present then. So having made my first point, I can now go to the second. Objectification allows us to do more things with a smaller set of tools. In the previous module, I claimed that research, whether mathematical or any other, provides us with stories that help us in deciding about how to act. More precisely, these stories mediate all our activities. I will now unpack this statement by showing how stories on numbers can mediate our activities with concrete objects. I will do this with the help of an example that can appear overly simple, but the simplicity is its strength as it shows the mechanism of mediation with particular clarity. In this example, the interviewer says to the interviewee, the 18-year-old girl by name Myra. He says to her, you bought 3 cookies from me. Each one costs 75 agoras. Agora is the Israeli monetary unit, such as cent or penny. Now you have to pay me. Myra has some real coins at her disposal. Here is the conversation that followed. 3 times 75, she says. 150 plus 3 times 25. 75, 150 plus 75, 225. Here you are, 2 shekels and 25 agoras. While saying these last words, Myra passes 2 coins of 1 shekel, which is another Israeli monetary unit, such as dollar or pound, and then she adds the set of coins composed of 2 coins of 10 agoras and 1 of 5. Let me take a close look at what Myra said and did. Myra said 3 times 75. This statement is the translation of the required operation of composing the appropriate set of coins into the numerical operation on numbers, the one of multiplication. Myra took 50 out of the 3 75s and added them together. How do I know that this is what she did? Because in the next move, she multiplied by 3 the remaining 25s. And then she added the 2 intermediary results, obtaining 225. Let's take a look at what happened in the conversation as a whole. You can see here that in the beginning, the talk is about concrete objects, cookies and coins. Then Myra makes a transition to mathematical objects, numbers. In the end, the conversation goes back to concrete objects, coins. Note that in the last sentence, the number names 2 and 25 are but labels for coins. The coin of 1 shekel and the set of coins, including 2 coins of 10 agoras and 1 of 5. I will now help myself with a diagram to present the path followed by the interviewee. The conversation began in the discourse on concrete objects, the coins. The first step was to move to the numerical discourse by translating the coins into numbers. The second step was performed in its entirety within the numerical discourse. It was an operation on numbers that produced the narrative 3 times 75 equals 225. The third step was to translate this narrative back into the discourse on concrete objects, into the act of passing the matching set of coins from the buyer to the seller. The monetary transaction, therefore, was a brief drama in 3 acts, with the middle one, the act of planning the action, resulting in the mediating story about numbers. But as I will demonstrate in one of the following modules, an action such as Myra's could be done also in a more direct, immediate way, all of it exclusively within the discourse on coins. In such direct action, one simply passes 3 sets of 75 agoras one by one. In this case, no mediating story is told, and the payer may end up without necessarily knowing the total price of the purchase. What is the worth of inserting the mediating action? Well, it is the universality of the resulting way of acting. When one acts in the direct, immediate way, one relies on her memory of the sets of coins that compose different basic values, such as that of 75 agoras. This way of acting is applicable only in situations involving money. But with the mediating action that translates the concrete objects into numbers, the same way of acting may be appropriate for another situation with objects of a different kind, say weights. Mathematical objects, therefore, make a person able to act also in situations that are new to them that is, involve objects, concrete or abstract, upon which they never operated before. This completes my attempt to present cognitive answers to the question of why we need mathematical objects. You may now proceed to Module 5, devoted to ways in which mathematical objects are constructed by mathematicians and then also by students. Thank you.